First keynote today is by Professor David Keyes. David Keyes is a professor and founding dean here at KAUST, where he leads the Extreme Computing Research Center, and he's also an adjunct professor at Columbia University. He's a renowned expert in scalable solvers and high-performance computing, and he's a fellow of several societies such as SIAM, AMS, and AAAS. His distinguished career includes winning 2 Gordon Bell Prizes in 1999 and 2024, the Sidney Fernbach Award, among many others. And has been also named by HPC Wire as one of the legends of high-performance computing. And I think it's fair to say that he is also one of the legends of KAUST. He's been really one of the, kindest, brightest, and most popular faculty members here at KAUST. So without any further ado, I would like, please join me in welcoming David.
Well, that's a lot to live up to, Ibrahim. But being enabled to address this amazing gathering of machine learners today is an unexpected blessing. If I can be said to be a machine learner, it's primarily in the old sense of the term, using regression on data to train a statistical model on an X to Y maps from which new Y values can be inferred at X's where data was missing. My use of more contemporary modes of machine learning, including neural networks, is recent and limited to collaborations with experts like you, where more mainstream learners rely on algebraic compression methods that we have developed, including algebraic low-rank structure and low-precision arithmetic, actually the latter being designed for the contemporary machine learning hardware marketplace. So you can see my title, and I'll get into that in a moment, but I just want to mention that in parallel with this winter school, KAUST is hosting another conference this week in a smaller auditorium nearby with many Chinese, American, and European National Academy members and a Turing Award laureate on a related topic, the mathematics of data science. And since I'm a co-organizer of that conference, I will be disappearing after my talk here today. However, I'm happy to meet you during our mutual lunch break in the diner. Just come and interrupt me whatever I'm doing, and my guests will be very happy to meet you too. So find us today in the same environment. There's a convergence today of the 3 paradigms, the 3 ways of knowing by computer, simulation, analytics, and learning. So we're at the fortunate point, the sort of synergistic point, where improvements to any one of these methods is rapidly improving the other 2. For example, simulation benefits from data analytics by steering in high-dimensional parameter space. Which expensive simulations should you run next rather than running them all? And also from some in-situ processing of data so that we don't have to go back and forth to disk, but just isolate during the execution when it's all in fast memory what you're looking for. Machine learning has been essential in speeding up simulations by replacing expensive constitutive laws with learned functions. The outer method is still simulation, but a lot of the innards have been replaced with surrogates from learned data. And then there's, of course, smart data compression. To analytics, simulation does a valuable thing. It provides physics-based regularization of all of these plausible results, which ones, for instance, satisfy the conservation of energy, momentum, and so forth. And machine learning provides detection and classification and imputation of missing data. And to learning, simulation provides the great service where data is sparse, whether it's because of expensive experiments or small sets of patients or whatever. It provides training for data, augmenting whatever real-world data you have. And analytics can clean feature vectors used in training. So traditional simulation systems don't learn. They are a model that was posited by a scientist, and their inputs come and outputs come, and the real future that is very exciting now is the interaction between classical simulation models and analytics and learning in a virtuous cycle where the simulation produces data from models, the learning produces models from data, and that can improve the models and greatly speed up. And I think both of them working together, at least when it comes to physics-based models. Of course, social models, we don't have such things as conservation laws, but when it comes to physics and engineering, the future is a fusion of machine learning and simulation. So I'm going to be talking a little bit today about a Gordon Bell Prize. Here's Gordon. He lived to 90. We lost him a year or so ago, and he was the founding director in the United States of the Office of Computer and Information Science and Engineering, following a very successful career in machine hardware. And he instituted a prize, and it was originally any area, and then it went to COVID modeling, and then it went to climate modeling. And a team from KAUST, a team led by KAUST with NVIDIA and NCAR, the National Center for Atmospheric Research in the US, and some other universities, actually won that prize last year, and led me to be thinking a lot about the prize itself, and what should it measure? We won it for operations per second. It's a speed test, basically, for a real application. And if operations per second, what kind of operations in the mixed precision machine learning oriented GPU era? Traditionally, it was double precision floating point. And given its potential for focusing the attention of both researchers and vendors, what metrics might be better than just double precision floating point? And can such benefit of all that focused attention on a traditional prize be extended to machine learning? And how might it adapt further to this coming hybrid classical quantum era where what's the equivalent of flops when you're talking about quantum circuits and the flipping of qubits? So I'm going to give a few perspectives from the first 37 years of the prize, promote discussion of how the prize should be curated, and attempt to answer not for what the bell tolls, the traditional question, but for what should the bell toll. So for what has the bell tolled? Well, back in 1987, a computer scientist named Alan Karp posed the question, could any practical code actually achieve a 100-fold parallel speedup? And that Karp Prize the next year became the Gordon Bell Prize for peak performance, and that prize has been awarded every year since. But there have been a variety of other special Gordon Bell Prizes that came up for different notable achievements that weren't necessarily the fastest speed test, but something that led to great progress in parallel computing, especially in the simulation side. And then, as I mentioned, COVID and climate were focused attention of Gordon in his last years. And since Gordon himself and the committee that he has appointed tinkered with the prize over the years, I think it's not irreverent for us as onlookers to do the same. So time to solution, I mentioned, it sort of was in boldface near the bottom. Our first few submissions to Gordon Bell focused on time to solution, the time to solution addresses, the big problem of computing today, which is we're running out of energy to spend on it. The #1 system in the world today, ranked in the top 500, delivers about 1.8 exaflops, 10 to the 18th floating point operations per second, at about 60 gigaflops per watt, the energy efficiency, and that's about 30 megawatts consumed continuously if that were 2 exaflops. And the representative cost of electricity in the US is about 20 cents per kilowatt hour. So this machine is that means it's $200 per megawatt hour, which means this machine costs about $6,000 per hour. And at about 10,000 hours per year, that's a $60 million electricity bill, which is actually small compared to some of the hyperscalers. But the carbon footprint of a kilowatt hour is about half a kilogram CO2 equivalent, no matter how you derive it. And so the El Capitan system is about 15,000 kilograms of CO2 per hour just to flip bits and communicate those bits across copper and optics and so forth. So that's 150,000 metric tons annually, which is equivalent to about 30,000 passenger cars driven average miles and average miles per gallon in the US. So even a 10% improvement in energy efficiency is equivalent to taking 3,000 cars off the road and saving $6 million per year. If you could do a 10x improvement, you would save 54 million a year and take 27,000 cars off the road. And 10x, I mean, is actually achievable in many use cases where the core of the computation is linear algebra. There's another sort of graph about the energy elephant. You see on the left, about 10 years ago in the US, all of computing was estimated to take about 2% of the electricity grid, and especially with the rise of hyperscalers, the kind of work you do in machine learning, but also the growth of supercomputing in general, that is rising exponentially, and it's forecast to get up to, well, you see there, about 12%. Yesterday I heard Jürgen Schmidhuber in our symposium say it's heading towards 20% by 2030. And that's, you know, an enormous amount of cost and carbon footprint. This chart comes from the US Department of Energy, which is chartered by Congress to analyze electricity use on a periodic basis. And these are some of the, you know, sort of turning points. Individual data centers consume more power than El Capitan, about 100 megawatts, which is like a city of 65,000. And it's so desperate to try to obtain that power at any price that many of the hyperscalers, including Google, are making alliances with the nascent fusion energy industry. Google has already purchased 200 megawatts per year of power from a reactor that doesn't exist yet, but they have invested in it on the assumption that it will replace some of their electricity demands by the year 2030. So you have a choice, machine learners, you know, 30,000 cars or one computer, one hyperscaler. So science per joule, or whatever you want to get out of you know, your machine learning, inferences per joule, is a matter of planetary stewardship. Now let's put this in a little bit more dramatic terms for those of you that flew here. The carbon footprint of 1 passenger hour of commercial cruise is about 1/4 of a metric ton of CO2. So 1 hour of exaflops is equivalent to those people on your typical you know, passenger airliner to run. And so carbon offset your next flight by more efficient programming, or better yet, from a selfish point of view, carbon offset my flight back here by learning something from this talk, by taking away at least one thing. Now, a couple of years ago, with Turing Award laureate Jack Dongarra, we wrote an article that was commissioned by a physics journal on the Gordon Bell Prize, because they noticed that, and on this chart, you see the performance in flops per second in red squares of the top machine on the top 500, and in blue circles, you see the Gordon Bell Prize winner for that year running alongside and keeping a pretty good track of this benchmark. The benchmark is pure, but these are real applications: seismic, climate, cosmology, chemistry, and so forth. And we were going at about 1,000x per decade until we hit Dennard scaling ending, where you couldn't increase the frequency anymore because of the heat dissipated on tiny copper wires as you miniaturized. But the physicists noticed that a majority of the Gordon Bell Prizes had actually gone to physics type applications, so they commissioned this article. And it's interesting, of course, top 500 is non-decreasing. You just pay more, processors evolve, and you get a bigger computer. Gordon Bell has 9 times failed to exceed its own precedent because the application changed, and some applications are less amenable to using the flops provided by the hardware than others. It's interesting that in 2 cases, Gordon Bell peak performance exceeded what you could buy commercially, and those were 2 special machines made just for an application: Grape for cosmology and Anton for molecular dynamics in drug discovery. But the ratio of the Gordon Bell winner for a given year in the top 500, because of those 2 exceptions, ranges from about 9% to 160%, with a median of about 50%. So the prize for real applications is tracking the vendor provisions reasonably well. So during my time at KAUST, and especially in the last few years, we have 4 times been a finalist for the Gordon Bell Prize, and in 2024, we actually had 2 finalists. Now, there are 6 in the world in any given year, so we were very proud to be named a finalist. Finalist is really the prize to me. It means you get to give a talk at Supercomputing. Of course, if you also win the prize, your team gets to divide a small amount of cash, but it's really more important just to get to the podium. And these are the applications that we entered, but interestingly enough, it was all the same algorithm, more or less. It was turning a dense linear algebra problem into something that was data sparse. So in 2022, the chief bottleneck of our spatial statistics, which is, kind of a machine learning problem, was tile low rank, mixed precision, and dynamic runtime systems. In 2023, we just used tile low rank on a frequency domain seismic problem. And in 2024, one of our applications was genome-wide association studies. You monitor the health of several people whose DNA you know. You have other people whose DNA you know, but whose health you need to predict, and that's called genome-wide association studies. It's a very large linear algebra problem, depending on the size of the population and the size of the DNA. For humans, we're about 3 billion base pairs in our DNA. By the way, we're now working on wheat. Wheat is more complicated than humans. Wheat has 18 million base pairs instead of 6 million. So it's a bigger computing problem to figure out how we're losing so much of the world's wheat crop every year. But that's another story. As the climate changes, that is. And climate emulation was our prize-winning computation where we used mixed precision and dynamic runtime. So the first year was time to solution. Second year, we proposed memory bandwidth. And then last year, we actually had speed entrances, and that's what won. So computational efficiency through tuned approximation is my theme. It wasn't originally going for the highest performance because we were eliminating all the flops we could. There's a traditional method, which is n cubed, and or order n cubed flops in the problem size, and we were squeezing out as many of those as we could while getting the accuracy that the application needed. So in some sense, we were contrarian to the best metric for the prize. But something very interesting happened in 2024. While we continued on our time to solution, squeeze out the unnecessary flops, NVIDIA was our friend. NVIDIA was making low precision flops so much faster that by switching our matrices to lower precision in blocks where that could be afforded without an accuracy loss, not all of them, but some of them, then we were able to take advantage of those superlinear hardware speedups and get good rates starring floating point 8 in some cases and integer 8 on the Grace Hopper superchip. And that was done in the machine Alps in Switzerland. Now, there's a folk definition of insanity that you've probably heard before. Insanity is doing the same thing over and over and expecting a different result. So were we insane? By the way, this is sometimes attributed to Einstein, but it was actually first appearing after he had passed away. But our version of insanity, our contrarian behavior, paid off because although we were doing the same thing over and over again, the world was changing. And this is certainly a theme of today's researchers. Your computer systems of the future are not going to necessarily look like those today. In the US, we had a saying from Wayne Gretzky, a good player plays to where the puck is, while a great player skates to where the puck is going to be. There's not a lot of hockey in Saudi Arabia, so I've switched my metaphor to the falcon. I fly not to where the prey is, but to where it will be. It's actually well known now that falcons do calculus in their little brains. They don't fly towards the prey that they're going after, the snake or the bird or whatever, but they see where it's going and they deflect their motion to get there where it's going faster rather than just tracking where it is. So that's our philosophy of computer algorithm design to track where the architectures are going. And where the architectures are going, of course, is that arithmetic is very cheap compared to moving data, and the more you can shrink your data set size and the less you have to communicate it up and down between registers and cache and DRAM, and the less you have to spread it across a network, the more efficient your computation will be. And our journey towards this Gordon Bell Prize really began in 2018 with this figure. This is 128 lines from left to right, green when we're doing useful computing, red when we're idle, And that particular matrix computation took about 18 seconds on 4 nodes containing 32 cores each of our Shaheen computer system at that time. But we developed a low-rank algorithm to replace that one, which gave us the same accuracy to the number of digits needed, but ran about 10 times faster. And there are several things that you might not like about the bottom picture compared to the top one. First of all, it scores a much lower percentage of peak. We've squeezed out a lot of those flops. It's running red in some sense. Everybody's waiting for a small number of things to do. It has a poorer load balance among the 128 cores. It scales less efficiently from 1 to 128 cores. But despite those metrics that look like it's not a successful computation, it's 10 times faster, and it uses about 65% of the power during that 1/10 time, so it's really about 15 times more energy efficient. And to us, that was the metric that we were going for. So algorithms today have to span a widening gulf between ambitious applications, which are increasingly irregular, dynamic, unstructured, and austere architectures, like all the vendors want to sell you, which get their high-performance numbers by being optimized for uniformity. And in between those two diverging extremes are us, you and me, algorithm designers, and that means it's a full employment program because this stretching is getting worse and worse. So a little picture of what we did. This is the bottom triangle of a square symmetric matrix. Since it's symmetric, we only have to store and operate on the bottom triangle. And normally, one would fill up all those blocks with dense matrices and double precision. And what we were able to show was we could replace most of the off-diagonal blocks with a product of 2 matrices which were smaller. In other words, it's a low-rank block. We still were using double precision, and we were adapting to where that rank was more effective, full, or exploited. At the same time, we realized that not only was the data smooth off the diagonal, but it was small off the diagonal. So if you combine, a high precision, a large number with a small number additively, most of the mantissa of the small number will fall off the end. And so you might as well only store the part that is significant with an appropriately normalized exponent. And so adaptively, we could estimate by comparing norms of different blocks which ones we could assign to low precision tensor cores instead of the full double. And in the end, we ended up with a matrix data structure, which is very complex to code, but very efficient in terms of both time and energy, while providing an acceptable answer that could be, we can adjust the accuracy. The number of vectors we choose in the rank, the number of blocks that go low, we can choose adaptively to attain the accuracy that the user wants. And so the main goal is don't oversolve, but almost more important is don't overstore, because when you move data, that's where the energy bites you. And we're now using 4 precisions on our wonderful Grace Hopper processors, double, single, half, and quarter precision FP8. Of course, Blackwell offers FP4. We haven't dared to use that for scientific computing yet. But the secret sauce of this new linear algebra is, where possible, without losing accuracy, replace default double precision with some of these new lower precisions. They might be IEEE, they might be BF things, like Google is using. Save storage, save data motion, and exploit the special purpose hardware. And also replace the full rank blocks of discrete linear operators and discrete data. It's not just the matrices that have smooth regions that can be replaced low rank. Often it's continuous data from a visual or from some field of data like temperature in a region or something. There you also save storage, save data motion, and exploit the special purpose hardware designed for the basic linear algebra subroutines, BLAS. So the Renaissance consists of 2 pieces, just to repeat: formally dense matrices arising from many applications, and I list a number of them, including kernel matrices from GWAS and machine learning. Those can be very often replaced in most of their off-diagonal blocks if they are well ordered. Random matrices don't compress in this way at all, but if you have matrices coming from physical causal systems or physical images, very often this compression comes along for the ride. And matrices arising in applications often have blocks of large norm and small norm in the same system. And there's a long history in numerical linear algebra of exploiting that, over 60 years, because floating point was the expensive part of early computers. Now it's the cheap part compared to data motion. But we have a history of such preoccupations, and now we're returning cyclically to those years where we want to save on precision, not because of the cost of computing, but because we can fit more data in higher levels, faster levels of memory. So this might bring to you two natural questions. Have we been doing a stupid thing, for 50 years by focusing on double precision? When do we need to be cautious of low precision? And what is the intuition behind low rank? And when can we expect it to be practical? Not everywhere, and maybe not even in a lot of neural networks. But these two concepts can be illustrated with one problem, and if you'll forgive me, I'll dive into a little bit of numerical linear algebra. That is a very simple tridiagonal matrix which represents the Laplacian operator. It represents taking two derivatives of some smooth function. You put that function on a grid of points, and you apply this matrix to that, and it's equivalent of detecting the curvature of that smooth function at every point. And that is actually something that comes up very often in computational science and engineering. It's the basis of diffusion, of gravitational potential, electrostatic potential, temperature migration in a conductor, and so forth. And it turns out that that matrix has a condition number, a ratio of largest and smallest eigenvalues that grows quadratically in the size of the matrix. If you have n points on a line and you increase n, the condition number, the spread of eigenvalues from largest to smallest grows quadratically in n, which means that a problem doesn't have to be very large before that ratio exceeds the precision of a floating point system. So, in fact, GPUs were only accepted into my business in 2010 when they began to offer hardware double precision. They actually started that in 2008, but we first used them in a supercomputer in 2010. And there are some operators that come up often for which even double precision isn't good enough. So the cautionary tale is, don't expect to go around replacing all of computational science with low precision. But in many cases, it works. And these two ideas of low precision and low rank can be combined in this, for example, 1 million by 1 million covariance matrix, where you see 5 different colors of the blocks, and on the diagonal we need to use the default dense double and near the diagonal, but as the causal correlations become further apart, we can get away with all kinds of numerical crimes. And once again, the goal is fit more data in high, fast levels of registers and memories. So the original would have been 4 terabytes. 1 million by million is 1 trillion, times 8 bytes per word. That's 8 terabytes, divide by 2 for symmetry, 4 terabytes. That replacement matrix, which works just as well, is about 1/4 of the size. And you have some tuning knobs here. You can replace dense blocks with low rank, keep high accuracy, go to low. You can consider hardware parameters. What's your block size? You have 32 threads in a warp? That's a good size for a block. You have a certain amount of cache at this level? That's a good size to calibrate your block. So it's actually a wonderful algorithm that can semi-adapt to varieties of hardware. And you can select from a large menu of subroutines that produce these low-rank approximations. I'll list a few of them here. The standard singular value decomposition is too expensive. In the block size, it's n cubed. The randomized SVD replaces one of those n's with a log of the rank, and that's a very rigorous algorithm which guarantees you an accuracy. There's a cheaper one that actually came earlier called adaptive cross-approximation, which replaces 2 powers of n with rank and the log of n. And then there's all kinds of new methods called matrix skeletonization, and in these, you as the smart user extract a subset of rows you think are important, a subset of columns you think are important, and you build a replacement for your big matrix A consisting of your favorite columns and your favorite rows, and you fit a matrix U in between them so that the triple product, CUR, approximates A in some norm, and that gives you some equations to determine the elements of U. And this is a very rapidly evolving interpolatory kind of way of replacing big data with small data. So with these tricks, we can do a lot of science that's important to KAUST. We can do geospatial statistics, PDE constrained optimization. We're actually on sky in Hawaii with a Japanese telescope to correct for atmospheric turbulence, to spot remote objects like exoplanets of other stars. We can use our hierarchical low-rank matrix multiplication to decode wireless signals. We can use them in chemistry and material science to compress long-running applications that don't scale very high in parallel processor number, and again in genome-wide association studies. So I'm going to focus in the time I have with you today on primarily one area, which is covariance matrices that come up in climate and weather applications, which are typically modeled not by neural networks, although neural networks are successful, but they're very big, trillions of parameters. It turns out that because of the physics of continuous media like the atmosphere, you can get by with much smaller parameterized systems that wouldn't work for doing movie recommender systems, but are traditionally very efficient in statistics. And the goal is we have a loss function L and a parameter set theta to be tuned to data. The data is the z vector. It could be 1 million temperature measurements over some continent. And what you see in sigma, that's the covariance matrix. That's how our two temperatures related to each other at different points. And we need to invert that matrix, sigma to the -1, and we need to take the logarithm of its determinant, and that's one evaluation of L. So evaluating L every time is very expensive. It involves building a matrix, inverting it, and multiplying it with those z's and so forth. So we invert it with a Cholesky factorization, and these are some of the forms of the loss function that are used in statistics with different numbers of parameters. Some are space only, some are space time. We're not going to go into them, but let's take a very simple one, which is just the Gaussian decay. We have a pulse of a certain magnitude representing the correlation, and we have some random points in 2 or 3D, and we put that into a succession of 3 generations of x86 hardware, Sandy Bridge, Haswell, Skylake. This is an old chart from 2018, so you'll forgive the use of ancient hardware that probably some of you haven't ever even used. But there's the n-cubed algorithm. This is a log-log plot. So that dashed line shows that the traditional method costs n-cubed as you make the problem size larger. Runtime down is good. And our algorithm is not only lower slope, that's the n-squared we promised you, but it starts lower. It has a better constant. So you have a choice. You can wait for Intel to give you a better chip, or you can, on the old chip, you can use a better algorithm. And it's much better, of course, to fix the algorithm than to wait for the hardware. Of course, you can do both if your algorithm ports across the generations of memory hierarchies. And that's what we've been doing. Now, that was the runtime. Here's the size. That black line, which is independent of the accuracy threshold, that's using double all the time. But if you set your accuracy threshold and you downgrade the quality of the precision, you get those green and red curves, and you can save 1 or 2 orders of magnitude depending on how you tune your accuracy. That was for shared memory. This is for distributed memory. Our second supercomputer here at KAUST was a Cray with tens of thousands of cores, 6,000 compute nodes, each of which was 32 cores. And here you see a computation on different numbers of nodes. So we started off with 16 nodes, and by using 256 nodes, which is the dark green curve, second from the bottom, we could go faster. Of course, this is again a log-log plot, but by switching the algorithm and sticking with those original 16 nodes, just use a tiny part of the computer, we could get much better performance than using a big chunk of the computer. So we could let other people run on the rest of it. So, you know, there's two motivations for mixed precision. Statisticians faced with problems this large actually set a lot of their blocks to 0. We say, no, that's too you know, risky. That's too far from the real model, but you can use low precision. So you get the benefit of shrinking the problem without sort of destroying the problem. And there's also faster time to solution. And NVIDIA and other GPU vendors, AMD and Intel, are leading us down this path. And you can see this from 4 generations of NVIDIA hardware, the Volta, the Ampere, the Haswell, and the Blackwell. And I'm plotting here the speed of, in teraflops of doing different precision calculations using different parts of the NVIDIA hardware. And what we get is superlinear. You drop the byte ratio by a factor of 4 from FP64 to FP16, but you get a speed up ratio not of 4, but of 8. And it gets better as NVIDIA optimizes for machine learning. And in Blackwell, which is out today, going from double to half precision gives you a factor of 225, not a factor of 4. Sorry, 125 there. Now notice another feature. NVIDIA felt it could afford to downgrade double. Double performance decreased. That never happens in my industry. You know, you're always getting a chip focusing on speeding that part up. But NVIDIA said, hey, people aren't using double in my industry, you know, in machine learning. We'll still supply it in hardware, but we'll devote less real estate to that part of the chip. And now, you know, I'll show you that plot again, but now I'm looking at 2 new rows that come in with Hopper and Blackwell. Hopper gave us FP8. We used that in our Gordon Bell Prize. Blackwell gives us FP4 if we think we can use it. And there's the 225 that was in my memory for this slide, going from double to 1/8 precision. So, yeah. Oh, is that okay? But we started at 10:15. I mean 9:15, right? Oh, okay. So I'm being asked to speed up, so I'll save some of the repetitious aspects of demonstrating things to you, and I'll just give you movies of our Gordon Bell papers. So this was the 2022 paper for spatial statistics. This was done with Jack Donguera, the Turing Award winner who's here today, whose group developed the dynamic runtime system that we needed. Why did we need dynamic runtime? Because when we exploit all this non-uniformity, blocks of different size, rank, blocks of different precision, all the load balance gets spoiled. You can't predict when a given block will be ready. So we needed a runtime system that would move data around and give us full exploitation of the cores. And in the bottom row are our KAUST statisticians and computer scientists. And I'll skip the demonstration that we win, but you can see in the red box there, dense double, mixed precision dense, mixed precision tile low rank. We basically get the same mean square prediction error with our much cheaper method. And this ran on the world's #1 at the time, the Fugaku system in Japan. Then 2023, the seismic calculation, that was done with Cerebras, the new AI vendor that puts trillions of processors on one piece of silicon. So you see the Cerebras chip versus the largest GPU on the right there. And this is all processors in memory. It's a very innovative design. And we had to rely on 2 of the Cerebras engineers to translate our code into their assembly code. And on the right is Matteo, our geophysicist. But this was the work of my grad student, Yoshi Hong, who's now a professor at Indiana in the US. And basically, after we low-ranked all these matrices, we then could regroup them to make efficient use of the Cerebras. And with that Cerebras system, which only costs about $100 million compared to the Fugaku, which costs $1 billion, we got almost the same memory bandwidth because everything was living closer to the processors. And we didn't have to use DRAM. We could use SRAM only. and I won't go into this chart, but that was our claim to fame that year, that we beat all these chips, AMD, NVIDIA, Fujitsu, NEC, AMD, Intel, all of those had inferior bandwidth for the size problem we were running, and only Fugaku among the big machines of the world, we ran on 6 of them, and only Fugaku could beat us compared to this Cerebras cluster. So we're basically introducing machine learning designed hardware into the scientific computing realm. And Aramco's, of course, very interested in this. 2024, our Genome Association study, using 5 precisions. 4 of the people in the top row are NVIDIA people. They're not all NVIDIA hardware engineers. Some of them are NVIDIA genomicists. Did you know that NVIDIA is the new Bell Labs? I mean, they employ all kinds of scientists from different domains to try to move things onto GPUs. We didn't have a genomicist. We had NVIDIA as our genome scientists as well as our collaborators in hardware. And the gist of this is that you're given known patients with known results. You're given new patients with unknown results, but you know their DNA and their environmental habits, like do they smoke, do they live near a chemical plant, and so forth. So those are the purple blocks compared to the discrete DNA blocks. And the goal is to predict their phenotypes. Will they get cancer? Will they die at age so-and-so? And so it's basically a simple algebraic trick that converts differences of 2 vectors into matrix-matrix products, using something you've known since elementary school, that a minus b all squared is a squared plus b squared minus 2ab, but now a and b are matrices, and so we can get that difference from matrix multiplies. I won't go into it, but it was the part of another one of my students' best papers to convert that into DNA differences, and she sped up a DNA calculation. You have two long vectors. What's the difference between their nucleic acids? On an Intel Ice Lake, using the vector algorithm, it would have taken 40,000 seconds. That's like, well over 10 hours. Using int1, emulated on Ampere, it took 8 seconds. So that's a 4,000-fold speed up to get exactly the same answer. Different hardware, yes, went from CPU to GPU, but the main improvement is the algorithm, going from differencing to matrix multiply. And so I will skip this, but it's worth pointing out the kernel ridge regression was our mode in doing this genome-wide stuff. If you get a 1, you have perfect association. If you get -1, you have negative correlation. If you get anything positive, then you're imitating nature. And with ridge regression, we got like 0.3, but with kernel ridge regression, we got like 0.8 or 0.9. So we were very happy with speeding up that aspect of, we used the UK Biobank. So we got 2 exaflops on the integer stuff. We got 1 exaflops on the algebraic stuff, and we got 1.8 overall. And that was a very high number. But for the climate model, we got about 0.8 exaflops, and that was a winner that year. And here are our climate and statistical people. And climate emulating is important because it's the machine learning companion to solving the Navier-Stokes equations for the atmosphere, which is very expensive and doesn't fit well on modern architecture. But the problem with climate emulation is that the matrices are big. In PDE modeling, the matrices are sparse. So we actually took the scale down from about 100 kilometers to about 3.5 kilometers. We ran 35 years of data for training at 54 million spatial locations around the globe, and we were able to basically produce emulations that had the same statistics as the physical climate, and they can be run on a laptop. You do the training on the world's #1 system, but then once you have your statistical model, you can democratize climate prediction to the laptop. And I won't go into this chart, but the top is training, the bottom is inference, and basically there's a big Cholesky decomposition, that's our signature, and there's 2 spherical harmonic transform steps. Again, I've been told to save time for questions, so I will get to a few other topics. The good thing about Gordon Bell is once you get close, all the big computer systems in the world want you to run on their system before the deadline so that they can become famous, if you become famous. So computational infrastructure, it's demanding a growing part of our research budgets. So, and there are new algorithmic opportunities to mitigate that. And we advocate that instead of looking at raw rate of computation, yeah, you have to get the right answer, but you should really, at every phase of your computation, be limited by what is the most important bottleneck, whether it's flops, whether it's bytes of capacity, whether it's floats per bytes, you know, how many arithmetic registers can you activate at once, and so forth. So we advocate science per joule as the ultimate metric. We have a very efficient machine. It's in the top 10 for its kind of machine in energy efficiency in the world. It happens to be a machine with NVIDIA hoppers and AMD CPUs, Genoa. We've recently written a position paper on high-performance statistical computing, which we call the original machine learning. That's with KAUST authors and alumni. And I would just like to point out, because I know many of you are interested in quantum computing, that quantum is going to be very helpful. I'm not sure how helpful quantum is going to be for AI, but AI is going to be very helpful for quantum, because NVIDIA just created NVQ-Link, a hardware box that links a supercomputer to about a dozen different quantum processing units to do the onload, offload, and it's full of FP4 machine learning in order to do quantum error correction. So we're looking forward to a very productive fusion of these two technologies, one very well established, one very new. You see this paper from Berkeley, you can download it from September. And we're currently at the bottom left of this diagram. This is number of quantum gates. It's in the thousands today. And the number of qubits, which is today in the hundreds. And by the end of 2025, no algorithm that runs on a quantum computer is faster than a classical. But as you go out into more qubits and more gates, you're starting to get to algorithms where there's an advantage in time to going the quantum route, if only the physicists could deliver to us reliable quantum hardware. So my philosophy for the future is QPUs first. Wherever you can replace a subroutine with its quantum equivalent, that's where that comes in, but it's always integrated in a classical supercomputer with GPUs for structured work and CPUs for unstructured work. And the computer science challenge of the future is partitioning your workload into these three heterogeneous resources and navigating between them when there's many users using all three of them in the same batching environment. So, For Whom the Bell Tolls, a classic poem, which has this quatrain: no man is an island entire of itself, each is a piece of the continent, a part of the main. We're in an interdisciplinary world with simulation, analytics, and machine learning. We're in a multi-heterogeneous world with QPUs, GPUs, and CPUs, and they all have to somehow work together. So how prophetic of high-performance computing. We want not just to compute sustainably, but we want to compute sustainable applications here at KAUST, and these are two of the Sustainable Development Goals that we have adopted as targets for the university. My final remark is, do linear algebra, see the world. If you're good at linear algebra, you know, you're needed by everybody. This is a poster from, you know, recruiting for the Navy in World War II. You know, join the Navy and see the world. Well, don't join the Navy. Do linear algebra, and you will see the world. There are some references, and I'm very happy to sit for some questions, as well as see you at lunch. Sorry.
Okay, thank you so much, David, for the exciting talk. Maybe before we start the Q&A, I just wanted to say that we have another talk at 11:45 about using AI for weather forecasting.
Oh,
so,
yeah,
yes.
which has been very good on Gordon Bell finalists also. Yes.
Yeah, so that's...
Is it the Pangu software, or is it?
No, it's the weather, what's the name? GenCast?
I can look it up online, of course.
Yeah.
Hi.
Yeah, please go ahead.
Hello. Thank you so much for the talk. It's really a wonderful way to start the day, especially when you talked about the environmental impact of using such supercomputers.
Right.
You mainly focused on the carbon footprint, but I was wondering about the water footprint as well.
Oh, yes, actually, that's a very profound point.
Can I continue the question really quickly? Okay. So, for example, I looked up the water usage of the El Capitan supercomputer. It uses 5 to 9 million gallons of water per 24 hours of operation. So I was wondering, regarding making more efficient computers, how would that affect the water footprint?
Thank you so much for bringing up water. I have tended to neglect it, just focusing on electricity. But in fact, if you look at the way that hyperscalers are trying to get their plants accepted by the local communities, very often it's the water that is the deeper concern. And it has to, of course, be very pure water, because it's going to be, you don't want corrosion in the cooling system. And unfortunately, most of it is evaporated. We have to design cooling in the future, engineering cooling, where you don't actually lose all that water. You pump it out, you put it in the atmosphere, it comes down somewhere else, and it's a big disaster. So I really appreciate. I think I'll add a slide, or I'll try to find some numbers for that. Yeah, and in Saudi Arabia, where our water is desalinated, we get a double penalty because it's all that energy up front. Very, very good point.
Thank you so much.
Thank you. Thank you. So better algorithms, right? That's how we use less water.
Hi. Thank you so much. There's a lot to learn here. I have to look at the slides and actually go through all of the references. Just a quick question: when you design systems like this, and you are talking about the different type of computations, like as for example, KAUST has to deal with both scientific computations and also has to deal with the machine learning workloads. You are talking about lower precision, int4, FP4, and you're saying int8 and FP8, but we're looking at int4, FP4. Even some papers are like saying, well, 1 bit is all you need as well. How do you design systems that actually accommodate all of these different type of workloads? Some of them require 128 bits, some of them require 1 bit. Obviously, if you want to support everything, you will have very complex, very large system. You lose the benefit of everything. How do you make that trade-off? And where do you see us heading as well towards this weird 1-bit regime and 128 scheme?
Yeah. So well, yeah, your question just describes the great excitement that your generation has in terms of finding the right partitioning of a workload into all these different heterogeneous portions. By the way, your cell phone has about 40 different processors in it, and most of them are only used, you're usually only using one at a time. And we don't mind that we've replicated that hardware and hardly ever use it, because when we do use one part of it, it's very fast for us and it's very efficient for that task, like streaming a movie or doing prediction of the next word and typing a word. So when we look at a heterogeneous processor, I think we can't look at efficiency as how do we use everything at once, but how do we map to the most appropriate tensor core or whatever it is. You saw that we were down to emulating 1 bit for vector differences between presence or absence of a nucleic acid. And yet, as you mentioned, which I didn't even mention, sometimes scientific computing needs 128 bits. If you go, sometimes we need quadruple precision because of the poor condition number. So I think that it's rare that this will be automated. I think that, so within a class of applications, I'm sure that there can be a default, FP4 or FP8 for a lot of machine learning applications. But when you look at the whole range of magnitudes of numbers that come up in a large-scale problem, I think the user is going to have to get involved in choosing precisions. And in our case, we do it by estimating norms of blocks. But what that will mean for some other application is up to that expert. So it's a rich field for which I don't have any, predictions of how it's going to be done by compilers, by users, by whatever. But I would like to dispel the preoccupation that we have to use everything all at once efficiently. I think we really should be we might use the QPU for a few seconds and turn off the rest of the computer and then come back. You know, it might evaluate some energy of some molecule, and then we go back to the main computer to do the optimization loop and predict the next configuration and go back and forth. And so one of them is off, waiting for the other, and that's heterogeneity, and we shouldn't say, oh, that's inefficient. We should say, oh, that's very efficient, because the hardware we're not using, you know, may be useful by some other computation during the same time.
Very, very interesting. So you would offload the efficiency to the operating system to maximize it. Is this what you're proposing? Yeah. So you're saying we depend on the operating system to basically maximize the efficiency rather than try to change that in your hardware level. But then you can make a bet that is a wrong bet, for example, when you are designing the system, and say, I want to have these number of components that I will not be used 1% of the time, right? And now your hardware is obsolete because you're going to have to...
So, yeah, you call to mind an amusing point. Because of delays in procurement, our Shaheen 3 GPU system is actually using 2022 GPUs. But they're my favorite because they have 67 teraflops of floating point, the double precision. If we were allowed to upgrade, you know, NVIDIA says, oh, it's been delayed so long, do you want Blackwells instead? I'd say, not necessarily. So we hope we get like 7 years use out of these very efficient hoppers. But yeah, it makes not just the computer user, but also the provider, you know, the person who makes the strategic decision on investing. Yesterday at our other symposium, Bill Grupp, the head of the NCSA NSF Supercomputer Center at Illinois in the US, said, systems now are evergreen. You don't do a forklift upgrade where you throw away the old and you bring in the new. Every year you add, you know, a certain number of cabinets of the next generation. So by the time, you know, you're 5 years into an acquisition, within one integrated network, fast network, you have many different generations of hardware with different amounts of cache and speeds and so forth. So programming those, you know, how you want to use those is a real challenge, but, you know, defending them to your user is also a real challenge because the non-uniformity makes everything much more difficult. Yeah.
Thank you.
Thank you for your good question.
One final one on the quantum thing, because you mentioned it at the passing, and I didn't quite...
Too much in passing,
very quick in passing.
But,
should we be worried about the old system?
I don't think, if you're a machine learner, I don't think you have to worry about quantum just yet. It's not that helpful to you. But you can be a big help to quantum. Because, I mean, machine learning is helping everything. Machine learning is helping fusion, you know, and that's helping machine learning, right, with new power. There are now surrogates of several different fusion reactors made by machine learning, which are thousands of times faster than running the same simulation using magnetohydrodynamic physics. And what's the benefit for that? It's not only in rapid design iterations for fusion hardware, it's also for control of fusion instabilities when the hardware is running. So you have a reactor and it's about to go unstable, and a machine learning surrogate can detect that in, you know, some traces of some phenomena and immediately provide a correction that, you know, the computation on a supercomputer would take not milliseconds to repair the instability, but hours, and, you know, the machine is destroyed. So, so many places where machine learning is actually the accelerator for other things. And that's, you know, one of the prospects that makes me optimistic about both quantum and fusion.
Thank you so much.
So hello, hi Dr. David. It's an amazing presentation. I'm enjoying it very well. Well, I work on quantum distributed architectures. So how can you like run a quantum algorithm or a quantum circuit on different modalities, like different chips, photonics and superconducting, etc. And I know about the NVIDIA like supercomputer that does have some like connection to some quantum chips, like in the machine of quantum machines. Yeah. So I just want to know like a perspective about this. What do you think about it? Is it gonna be really the future of computing, or is it something else?
I think that your generation, I might retire before quantum becomes practical, but I hope I can hold out to watch it come in. Your generation, no question, you're going to be, you know, using quantum hardware for some aspect. And we don't know which of the 7 kinds of physics it's going to be yet. You know, superconducting, qubits, Majorana fermions, electron spins, photonics, neutral atoms, charged ions. We don't know which one of those is going to give us scalable, reliable qubits. But we know that quantum algorithms will be able to run on the earliest of those that does. And we don't know when quantum Moore's law will kick in, you know. Going from 1,000 qubits today to, you know, enough qubits to make Shor's algorithm for decrypting RSA, that could take, you know, 1 year. It could take 10 years after the first, you know, emergence of the winning error correction technology. So, one of the reasons I went so fast over it, I'm not sure how to tie it in to AI, but as a separate talk, I have a talk called the earliest application of quantum utility, and I go through the parallel development of HPC with what I see happening in quantum, and try to create you know, a set of expectations for quantum along the way that will enable it to ride the wave of Moore and Dennard and all those wonderful scalings that have brought us, you know, exaflops.
And I think, yeah, that's a really good point, because we do need a lot of AI engineers and scientists to be able to build the next generation of quantum computers. So yeah, I do agree with you.
Thank you.
Yeah.
And which, you mentioned you're a quantum person yourself. Yes. Are you with a company or a university?
At Niels Bohr Institute of Physics in Copenhagen.
Okay,
Yeah.
great. Congratulations. Good choice.
Thank you.
All right. Yeah, we're out of time. Sorry, I hope it's a quick question, please.
Small,
Yeah.
Hi, Dr. David.
Hi.
Thank you very much for your amazing presentation. I work in medical AI, and I just have a question. You mentioned that you follow a quantum-first approach. Where in medicine do you think we'll see that first? Will we see it in medical image processing? Will we see it in large language model use, electronic health records?
Did you hear the question accurately?
Can you just... It wasn't clear from here.
Yeah. Can you hear me now?
Yeah.
Perfect. So you mentioned you follow the quantum-first approach, and I was wondering, in the next 5 to 10 years, where do you think we'd see that first in medicine? Would it be drug discovery, gene therapy, maybe image segmentation?
Yeah. The earliest application where it will be winning. Yeah. I think many experts in the field believe, and in fact, if you go back to the 1981 paper of Richard Feynman, who first, you know, introduced the concept of a quantum computer, his thought was, we need quantum computers in order to do chemistry and material science. We need quantum for quantum, and all these other things like decryption and machine learning and the optimization in the finance industry and transportation scheduling, all these things that make headlines for why governments are paying huge sums to develop quantum and make sure it's sovereign so that it won't be export controlled away from them when it does succeed. All those applications are going to come second and third and fourth and so forth. I think the earliest successes will be in developing new materials that have, you know, that depend on actually quantum phenomena for their structure and properties, and that's already happening. There are various collaborations between quantum vendors and users, like, you know, the aerospace industry for corrosion and so forth, where materials design is beginning to migrate. I don't think it beats classical yet, but people are at least, you know, forcing it into that paradigm to develop the quantum side more quickly.
David, do you see any applications or potential applications in healthcare, like in the medical domain?
Right. So actually, let me advertise a little bit about Saudi Arabia. We, in collaboration with the World Economic Forum, have between 2024 and 2025, we have released 7 reports on the expected utility of quantum computing. And one of them is on healthcare, one of them is on supply chain, one of them is on information computing technologies, and one of them is on the financial industry. Did I mention that already?
Are these reports public?
Yeah. So these reports are all online. They're downloadable. Search like World Economic Forum Quantum Economy Blueprint or something like that. And in Saudi Arabia, they are released under the Center for the Fourth Industrial Revolution, which is a floor of the Kingdom Tower where, they have a collaboration with the World Economic Forum. It's part of KAUST as well. And Saudi Arabia is actually, the World Economic Forum has stamped out this blueprint, and Saudi Arabia is like their most significant uptake of this. Now, there's a few countries that don't need this blueprint, China, US, where there's already Germany, France, England, they already have a very significant quantum industry, and they are already quantum sovereign. But for all those countries that want to get there, before it becomes export controlled and, something that they'll be buyers instead of sellers, we're very much by the World Economic Forum's estimates in the leadership role there. So be encouraged. It's not going to bypass us without notice.
Thank you very much.
All right, thank you, David. Please join me again in thanking David.
Thank you very much, Ibrahim. What a pleasure. Enjoy the rest of your meeting, and perhaps we'll intersect with this other math and data science meeting along the way. Thank you.
Thank you.
Okay, thank you.